Good evening and a very warm welcome to the Black Hole. Today we are going to discuss algorithmic market design, which is an exciting interplay between mathematics, economics, and computer science. For it, we have Haris Aziz with us. He will join us on Zoom. A little introduction, a brief introduction of him. He is a Scientia Associate Professor at University of New South Wales, Sydney, Australia, as well as he is the director of AI Institute of the same university. His research interests lie at the intersection of artificial intelligence, theoretical computer science, and mathematical social sciences, in particular computational social choice and algorithmic market design. और इसी के ऊपर आज वो गुफ्तगू भी करेंगे. Moreover, his research has been covered by media outlets such as BBC, Scientific American, Sydney Morning Herald, The Guardian, and many more. The Australian newspaper recognized him as the national field leader in game theory and decision sciences in 2020-2022. We are very grateful to Dr. Sarmad Abbasi as well, who will join this discussion as a moderator. आप ख़ास तौर पे लाहौर से तशरीफ़ लाए हैं और बग़ैर हम वक्त मज़ीद लिए सिर्फ एक दरख्वास्त अपने सेल फोन जो है वो आप साइलेंट मोड में कर दें so that there is no distraction. And now, ladies and gentlemen, please welcome Haris Aziz and Dr. Sarmad Abbasi. Thank you.
Okay, you can hear me through the microphone. And Haris, can you hear me?
All good, I can hear you.
Okay, so this is a bit strange that I can't see your face, but we have to chit chat. So we're going to talk a little bit and then we'll hear your talk, and at the end we'll have some question answers. And so in this informal session, if somebody wants to ask a question, or you're welcome to do so, just raise your hand so they can bring a mic to you, right? Otherwise your voice would not be recorded, or it wouldn't go on the stream. So Haris, tell me a little bit about yourself. So I think you were educated in Lahore till high school, or?
Yeah, so I met you at LUMS, right? So that was during my undergrad. But before LUMS, I've been in Lahore throughout. I was born in Lahore.
Achha.
So I took my schooling from Beacon House, HSN College. Then I went to LUMS. After that, I went overseas. It's been a long journey. So I was in the UK for several years for my higher education. So for my master's, I was at Oxford. I was studying a maths degree there. Then for my PhD, I moved to University of Warwick. After that, I spent a few years as a postdoc in Germany, and then somehow I ended up in Australia, which has been a very pleasant experience. So for the last 10 years or so, I've been in Sydney. So that's been my journey. So I've traveled quite a few places.
So let me ask you something. Like, very few Pakistanis pursue theoretical computer science, right? I mean, it's almost nobody. So what made you go into theory rather than the other catchy stuff of systems where there's, glory and money, and it's much easier to make a living that way? So
well, Sarmad, you can take credit for at least part of this interest. So I remember that. So initially, firstly, at LUMS, I was already taking more theory-based courses simply because I felt like I was more comfortable doing fundamental mathematics, algorithmics, theoretical computer science at uni. But that was also a bit of a selfish goal, because that gave me a bit more time to do other extracurricular activities like sports. Because like taking more programming-based courses, or taking some social science courses which involved long essays, that typically took more time for me naturally. So naturally, I was inclined towards this area, and then I think. some of the interaction with you was quite important, because I remember you were sharing some. At that time, Kurt Mellon's LIDA program had just come out. You shared some nice graphical interface with LIDA and graph algorithms, and later on, actually, I was fortunate to interact and talk to Kurt Mellon several times at Saarbrücken. And then I remember one book that was suggested was this biography on Paul Erdős. It was a book called A Man Who Loved
Only
Only Numbers.
numbers. Yeah.
Now that's not a technical book, but it has a lot of small nuggets on which highlight some beautiful aspects of mathematics, and also has some nice biographical accounts. So it also has accounts of several other people who were quite influential in theoretical computer science during that time. This was a couple of decades back. So I think that already piqued my interest towards fundamental aspects of computer science. And then when I went to Oxford, that particular degree was mathematics and foundations of computer science. So that's very much it's a tailor-made degree for theoretical computer science. So that really was the foundation for exploring more theory. But I remember at Oxford, there was a lot of focus on theory B, which is more mathematical logic and formal verification.
Yeah, yeah.
And at that time, I found out that there were some interesting things going on in algorithmics, which had some interplay with game theory. So that was the time I started looking at PhD programs, which had a bit more focus towards these concepts, which were at least quite fresh at that time. And even now, I will talk about it in my talk, but there's a lot of interesting questions which come up at this interface between maths, game theory, and computer science. So I'll mention a few of those
So,
in my talk.
so did you also do a double major when you were undergrad in maths, or were you only doing computer science?
I basically took enough cross-listed courses that I think I could have opted for a maths or a computer science degree. But I was told by, by many people that if you want to be more employable, you need to take a computer science degree. Although at the end, since I opted for a research program, it didn't really matter. But at the end of the day, I got a BSc honors in computer science. It wasn't maths, but it was a very math heavy computer science degree. So I was always trying to take courses which were cross listed with computer science.
Okay, and so you started doing game theory, algorithmic game theory, before it became really big. You know, when was the Navanina Prize given to algorithmic game theory? Was it 2016 or something?
So I think right when I was doing a PhD, that was already a lot of things were happening at the same time. So the PPAT completeness result uh, by Papa Dimitriou that came out at that time. Then Tim Roughgarden's congestion games, Price of Anarchy, price that came out in mid 2000s as well. And then I remember that actually the this book Algorithmic Game Theory, it was launched at our university, so we were co-organizers of this wonderful workshop that happened, because my supervisor was he knew many of these researchers. So that particular program, it actually they invited all the authors of the Algorithmic Game Theory book. This was around 2008 2007. The book got published during that same year as well. So that really was a wonderful opportunity to learn more from the leading people in the field.
Okay, I want to talk a little bit about what I think is possibly your most famous result, or probably I know it the best, is the cake cutting, right? The envy-free cake cutting. I mean, when did you work on it, and how did you get interested in it? Was it handed to you by your advisor, or you got attracted to it on your own?
So like I was quite familiar with the problem. in computational social choice, which is all about making collective decisions. This is a classical problem, even in fair division, which is a very classical field on how to make decisions which are fair. Cake cutting is one of the fundamental problems in that area. So I remember I was already familiar with a very nice book by Stephen Brams and Alan Taylor, who wrote a book on fair division, and that book already gave me some background on the kind of problems that were open. But I think you have it in your profile as well that a mathematician is a machine for turning coffee into theorems. So the conversation regarding this actually started when I was a research scientist at an industry lab, a national scientific lab in Australia, which did give me a lot of academic freedom to do whatever I wanted. And one of our PhD students, Simon McKenzie, he and I, we love to have coffee together and discuss ideas. So often that's what I tell a lot of my PhD students as well, that stick around for coffee rather than having these very formal scheduled meetings in an office environment. It's better to have
Yeah.
at least give more opportunity for spontaneous conversations. So at that time, Simon and I, we had some initial ideas on how to attack this problem, which was basically an open problem regarding four agents. So
Right.
just for the audience, I'll just mention what this problem is. Basically, cake cutting is a metaphor or for an abstract mathematical setting in fair division. And the goal is that you want to get enough information or elicit enough information about what parts of the cake different people like, so that you can identify an allocation which is called envy free. And envy free allocation simply means that nobody wants to get somebody else's allocation instead of their own allocation. So at that time, we knew that for four agents, there was an unbounded protocol, which means that it could take arbitrary amount of time or an arbitrary amount of queries. And we started working on that. So that was around 2015, 16. And interestingly, then I went as an invited professor to Paris for a few months, and Simon is also half French, so he also followed. He also came to France. So, some of our months were actually spent in Paris thinking about this problem as well. And then when we found a solution for the four agent case, we wrote a paper, but extending it to arbitrary number of agents was much trickier. So it took us. We had some ideas, then we had to work them out, but it worked out at the end. And yeah.
So, I remember that in one of my class, I was telling them about your cake cutting, and then I told them that I, it takes what, n to the n to the n to the n to the n queries, right?
Yes, that's actually in many popular science articles as well. It's a bit of a running joke that this is Tower of Six Ends. But I just want to emphasize that this problem itself was motivated in the 1940s by some very influential Polish mathematicians, including Steinhaus. And in Steinhaus' paper, basically Steinhaus motivated this problem by emphasizing two axioms which are important. One is envy freeness, right? And the other is proportionality, which says that everybody should feel that they got at least 1 over n of the total value of the cake, where n is the total number of agents. Now, if you just go for proportionality, there are many simple moving knife protocols which can get you in linear time. You can find a proportional allocation. On the other hand, if you just go for envy freeness, you can actually get envy freeness in a trivial manner. You can simply say that I'm just going to throw away the whole cake. Nobody gets anything, and you get envy
Yeah,
freeness.
yeah.
So if you allow people to throw away some cake, but you do emphasize that you need to achieve both proportionality and envy-freeness, then actually one part of our protocol, which is much simpler, it already gives you in n to power n times 2 to power n, which is more manageable than tower of 6 n's, you can already get proportionality and interference at the same time. It's just that if you insist that you need to allocate the whole cake, that you need to do a much harder work and it gets much messier. But I just want to emphasize that if you just want to go for the two main properties that were motivated by Steinhaus, which are interference and proportionality, then actually only one part of this protocol can get the job done. It's much simpler, and you can get it in basically n to power n queries.
Yeah, but I just love the fact that it's a tower for six ends, towers of
Yeah.
6 n. One of my students, she said, "Sir, cake kharab ho jayega." And, and मैंने कहा बेटा खराब नहीं होगा because there will be no molecules and you'd still be cutting it.
Exactly.
So but I think it's a beautiful result, and in part I think the beauty of it is that the solution is not a simple function, not a I mean that's just beautiful to me. There's so many results. For example, my advisor Samaradi has this regularity lemma, right? Which is true.
Yeah, that's highly influential in computer science.
Yeah, but it's true for large graphs, right? And how large the graph has to be is absolutely useless for anything practical, right? But theoretically, it's one of the most influential results in graph theory. So, yeah. I mean, I think these are the really beautiful results that in some sense. I mean, the pure beauty is there, right? That you are solving the problem. Do you think it would be improved?
Well, I think they have been followed works where there are at least strict improvements, but they're not like significant enough that it doesn't cut down the running time in a dramatic manner. But people have been following up with follow-up work. There was even a work on looking at the problem where instead of cake, you are allocating something which is undesirable. It's called chore allocation.
Oh,
So people used very similar ideas, but still you have to do work to get it done. They did it in a very rigorous way as well. So that was by a few Iranian researchers who are based in America. They had some follow-up work. Then for 418 case, there have been concrete results where they cut down by a certain number of steps, but not in the dramatic way that you bring down tower of 6n to something which is polynomial time. For example, polynomial time is still an open question.
Oh yeah, that would be huge, right?
Yeah.
That would be a huge thing.
Yeah.
Okay, so I wanted to ask you one thing that one of the problems in Pakistan is that most people don't want to do mathematics, right? And okay, Hassan is saying they don't want to do anything, but particularly mathematics is our weak link. And how important do you think mathematics is in computer science? And here I'm not talking about your work, because that is mathematical, right? But in general, the rest of computer science. I mean, do you feel that people who come to Australia from Pakistan are weaker in maths or than other people, say, let's say the Chinese or the Indians?
Generally, I think we obviously from Iran and also even Bangladesh, India, there are certain centers of excellence which they are producing researchers, or at least graduate level students who are possibly better prepared than many Pakistanis. And I think this is especially the case for theory. Theoretical computer science is definitely the case in other mathematical grounding as well. I'm not sure about other mathematics areas, for example, analysis, real analysis, etc. They might be I'm not familiar. I can't say for that, but at least for my area, I think there's just not enough interest, as you said, and it's probably also the case that the way it's taught is very important, right? So if you want to highlight why what you're studying is important, that's, I think when I'm teaching, I keep giving the students really appreciate examples where some ideas which are highly abstract, how they are influential in solving some real world problems. Obviously that's not the main reason why we do mathematics, right? Because we also pursue beauty and elegance and timelessness. But I think for students who are very career minded, they do appreciate if you are giving them more examples on how certain ideas are being used at the backdrop of various applications, various systems, etc. So I think that's partly our responsibility as educators, and that we should be highlighting how many ideas are interesting. So I think, at least from my point of view, when I was at LUMS, you were very influential in bringing out the fun aspect of mathematical ideas. So that is very important, highlighting the fun aspects of mathematical ideas and also highlighting how useful those ideas are.
Okay, so let's go to the audience if there are any questions you would like to ask. Mike Dedingi.
Thank you, RS, for sharing your journey with us. You'll be very pleased to know that today, for the first time in the history of Beacon House, we concluded a winter camp that was targeted at middle schoolers and was solely based on AI, because you said in your introduction that you are director at AI Institute of your
Thank you.
university.
That's great news.
Yeah. So we would like to know more about that role. What are you doing over there? What the institute is up to?
Yeah, so basically, I'm currently the director of a very large AI institute. In fact, when we set this institute up last year, we have over 300 university academics. So these are professors or lecturers, etc. Over 300 of them, they are members of our institute. Now, what you'll be surprised about is that although we have a significant presence in computer science and engineering in general, many people are not trained computer scientists, they're not data scientists, they're not doing machine learning, but many of them are applying these ideas in their respective fields. So, for example, we have a lot of interest from the medical school. They want to use machine learning for diagnostics. There's arts and design faculty, which is using machine learning for creating music. So there's even one of our researchers who won the Eurovision AI song contest. So that's and they're using machine learning for creating new architecture designs, new music, and creative design. Then there's a lot of interest from the business faculty as well, obviously, because startups want to, and small and medium enterprise, they want to use AI. So our role as an AI institute is that when people in the industry have problems, they really don't know who to talk to, right? There are so many academics, so many research groups. So we provide a window into all the expertise that is present at the university. So we connect them with problems in industry, connect them with problems in government. But another thing that we do a lot is public understanding. So similar, just like Black Hole is doing their effort in public outreach, we conduct a lot of seminars and general events like book launches, public events. So there was even one event that we had last year, which was organized by Andrew Ning. He was the speaker. Many people might know him because of his famous Coursera course in machine learning. And he just wanted to come over to Australia for 24 hours. We advertised that he was coming 3 days before, and we had a full house of 1,200 students who were very excited to meet him. So obviously there's a lot of interest.
Right. Assalamu alaikum. So you mentioned that there was still work going on into speeding up your cake cutting algorithm. I have to ask, any idea if people have managed to achieve, say, a quantum speed up or something of the sort, or any advantage of, say, parallelization in general?
No, as I responded to Sarma, I don't think I keep up with the citations, etc., and also what's going on. There hasn't been so much breakthrough on exactly that problem, but people have been looking at some very interesting variants of the problem where rather than requiring that everybody should be not nobody should be envious of anybody else, what they look at is what is called a social graph. So that social graph might be a tree, for example, and basically the agents are vertices in a graph, and you only care about envy with respect to your neighbors. So that makes the problem different, right? Because now you don't have to worry about everybody else. And then people have been coming up with very nice, fast algorithms, for example, for trees and other simpler graph structures.
Okay, so my question is more about the history of this game theory. So we know that John Nash started this, but if we go a bit earlier, like John von Neumann and other John Conway, they also played in some interesting game like the Game of Life.
John Conway was much later.
Really? So can you see some connections between all these?
Absolutely. John von Neumann was already, he had a lot of contributions on game theory way before John Nash. So this was already in the 1920s. There were several very important observations that were made. And regarding John Conway, actually John Conway was my PhD supervisor in Cambridge, and they actually also invented some other games which became quite popular. So, and one other connection I know is that John Conway was actually the founder of one of the cake cutting protocols, which was for the 3-agent case. So that's called the Selfridge-Conway method, which is very elegant. It's very simple. You can explain it. It doesn't take too long to understand or even understand the argument, mathematical proof for that. So yeah, John von Neumann's book, which was co-written with Morgenstern, that's still the founding book for a lot of work on one aspect of game theory, which is cooperative rather than non-cooperative. So they had already set up a lot of foundational ideas on cooperative game theory in this foundational book that John von Neumann and Oscar Morgenstern wrote. And some of these ideas are highly influential in multi-agent systems. Why that's the case? Because they talk a lot about collision formation, and collision formation is very important nowadays when you're designing systems where you want robots or bots or drones or different entities to interact with each other, form teams, and solve complex problems. In many of these contexts, a lot of these entities might be autonomous. They might not be centralized. So how would you want to make them cooperate with each other? That's a lot of ideas from cooperative games are quite helpful in that field as well.
That's good. Thank you.
I wanted to ask, will AI be able to take over maths? Will it eventually do the mathematicians' jobs for them?
So, firstly, mathematical verification is already being used not just because of AI, but also SAT solvers are being used to come up with counterexamples. Machine learning techniques are being used to come up with suitable conjectures. So in that sense, a lot of the boring part of maths, which might be like dozens of case-based analysis, you can use a formal verification tool to do that. You can do machine learning to identify, zone into some counterexample which you've been looking for a long time, right? But maths is not just about like establishing whether a particular statement is true or not. It's also you need to convince humans why this idea, what's the intuition behind it, what are the ideas behind it. So that part is still very much a human endeavor. It's not going to be taken over just by machine readable code. So from that point of view, we are very far from uh, like AI overtaking mathematics. I think we should just treat it just like we're treating AI as a helpful tool. I think it should be the same case in maths. It's not going to be the case that AI is going to take over maths and is going to solve all our proofs and all our problems. At least I don't think so.
Haris, I wanted to share some small experience. So I asked a friend. I'm not at all, savvy about programs or all these things. So I asked a friend, ask AI to give an algorithm to find a basis for the quotient space. You are given a vector space and you want, and the first attempt was a disaster, but the second was okay. Then I
is it in chat? Is it a chat GPT?
I think he did chat GPT and one of them did AI. With AI, I think it was better. I think he was that made sense. Then I asked them to give. So you have commuting vector fields. Give an algorithm to find the canonical form, and it says let's first compute the Lie bracket. I mean the Lie bracket is already 0, and it just gave complete rubbish. Just as I mean if like our wives know how they know all our terminology, so it used all the terminology, but it didn't make sense. So that's how far behind it is at the moment. But why would you want to? Why would you want to do artificial intelligence to do everything? There should be some purpose, right?
Yeah, and one thing which people are struggling with is that many of these AI programs, they don't even provide any formal guarantees, and mathematics is all about formal guarantees, right? So if you're not sure about something, that's already very far from the kind of rigorous mathematics we want to pursue. So my point of view is that whereas machine learning might be helpful in helping us identify some potentially useful counterexamples or some potential ideas, we just need to use it as an aid, whereas a lot of the intuition or writing it out in a human readable way or understanding it better, that has to be done by humans.
So something like proof checking it can do. I think I heard that they verify this Thomson's all the about this Thomson big theorem on group theory. So
I think even the Kepler conjecture, the proof of Kepler conjecture was pretty.
Four-color theorem.
Peter Schwartz also had his results in liquid vector spaces verified.
Sorry, what did you say? I didn't understand.
I was saying that Peter Schwartz also had most of his results on liquid vector spaces proof verified on Lean.
Recently, Terence Tao also recently had a result, right, which was computer verified. He was, he mentioned it. It was like crowdsourced project. Okay, hello sir. Honor to have you with us here. So my question is related to AI again. So we know about the alignment problem in artificial general intelligence, that when we achieve AGI, how will we align it to human goals and human values so that it does not go rogue? So your work in algorithmic game theory, interaction between agents, intelligent agents, cooperation and non-cooperation, do you have, and you have worked on the social sciences as well, so do you have any insights regarding that problem? Because it is something we have to solve in the near future, because AGI is coming. It is almost inevitable now. It will come, some people predict will come in 15-20 years. So how will we align those intelligent agents, which might also become super intelligence, to human values? Many people have their own different approaches for solving the alignment problem. Do you have any insights from algorithmic game theory that can be applied to the alignment problem?
So there are several researchers from our community who have been exploring ideas or this bridge between a lot of wonderful work that has already been done in mathematical social sciences and how it can be applied to some of these fresh problems which are coming up in AI. So one particular example I can give is Vincent Konitzer. He's was at Duke. I believe he's at CMU right now. He has been working on that quite a bit. My own experience with the connection between mathematical social sciences and AI has been on this aspect where people are very concerned not just about alignment problem, but they're very concerned about how to make sure that AI problems or AI programs are fair or they're ethical. So that's where some of my work, which is on fairness aspects, comes into play, because people in social sciences, people in mathematical social sciences, social choice, fair division, etc., they have been thinking quite deeply. Especially, they've been thinking very mathematically about how to make fair decisions. So many of those ideas are now starting to take place in machine learning as well. I can give you one example. So, for example, in machine learning, clustering is one particular task for which there are k-median problem or k-median algorithm. There are many standard problems which do not really take into account how proportionally representative or how fair the solution is. The global objective is very much trying to minimize the sum of the distances, which might be quite unfair to, let's say, a minority of the points in a spatial context. So there are some ideas from proportional representation, which is part of the literature on mathematical voting, that has started to be used in doing clustering, which is fairer in some sense. So in fact, we have some recent work on this as well, which came out a few months back, which is revisiting the clustering problem and making sure that rather than just using traditional global objectives such as minimizing sum of distances, you still try to do some global optimization, but you also try to introduce some axiomatic properties which are inspired by proportional representation ideas in voting theory. So that's what we did. That was one of our connections, where we bridged this gap between mathematical social sciences and fairness in machine learning. But I haven't worked on the alignment problem, but I do know that people have been exploring it.
So let's have one last question if there's one, and then Haris can start his talk.
I'm a great skeptic. I'm a great skeptic of AI. And you talk about mathematics in the social sciences, and that scares me. And I would like to repeat a question asked by an old Greek fellow about 2,000 years ago, a little more. Can virtue be taught? Can morality be taught? So, how does mathematical algorithms are not enough? Not even in economics. No matter what, we already have automation.
Yeah.
We already have automation. Decisions are taken based on certain data fed into the machine or whatever it is. So this is happening all the time the last 30, 40 years. It will continue to happen. And the biggest advantage here is in war, in defense, in warfare, weaponry. But when it comes to human beings, they're very different people. And
I'll come to that. I'll come to that in my talk.
What I'm trying to say is, they are not just groups or clusters, they're also individual human beings. And you cannot apply AI or chat GPT to everyone.
Yeah, so firstly, I myself, although I do work on one aspect of AI, which is multi-agent systems, my approach to many of these problems is very rigorous, in the sense that we work on formal guarantees. Our work is very axiomatic. And I understand your concern that how there's a big gap between morality and decision making in machines, right? But I'll mention some of the ideas that have been used in, for example, when you're trying to make some computer algorithms or making some decisions which are important for humans, such as who gets an admission or who gets a donated kidney. And this is sort of a motivation for my talk as well. And you do have this concern that you want to do it in some principled way. What I'm going to do in my talk is I'm going to motivate an axiomatic approach to these issues, which is using some very nice ideas from social sciences, which are not very mathematical, but they do capture something which is desirable. Using that idea to then mathematically formalize an axiom, which is obviously, it might be narrower than a very general concept like fairness. Fairness is a very elusive and very abstract concept, right? But there are some very particular versions of fairness that you may want to pursue in particular contexts. For example, in cake cutting, we discussed this aspect of what is called envy freeness. Now, envy freeness is captures a human psychology that you do not want. You don't want to be so dissatisfied that you say that I would rather have somebody else's allocation rather than mine. Now, that idea actually can be formalized in a mathematical way as well, and you can use it as a guiding principle to make decisions which are very algorithmic, right? So there are contexts where some ideas which are related to ethics, philosophy, fairness in a very abstract way, you may have some narrow versions of those definitions, and you might want to pursue them in a particular algorithm. An interesting thing in machine learning is that people have been formalizing so many different versions of fairness aspects, and there's one paper which has 21 different definitions. And what it shows is that actually many of these concepts are incompatible with each other. So it's really up to the system designer, it's up to the stakeholders to pursue or understand that which version of that fairness concept they might want to pursue for a particular application. And that has to be decided by talking to the stakeholders and talking to the policymakers. So in my talk, I will try to at least partially convince you that this axiomatic approach to coming up with some mathematical axiom which is inspired by concepts in mathematical social sciences, those can be used as guiding principles for principal decision making in computer science.
Okay, so let's stop here. So let's have the technical talk, and if there are other questions, then we'll. This wasn't the talk. No. No, this was a chit chat, but it went on for I think about 45 minutes. 40 minutes.
Shall I start, Samad?
Yeah, let's start.
All right, so this is an invitation to a field called Algorithmic Market Design. It could well be also algorithmic game theory or computational social choice, but the kind of case studies that I will mention, they are in the realm of market design. So that's why I mentioned that. And what I want to highlight is that this field, which is quite rich and it has a lot of important applications, it has had input and it has had ideas from many different research communities, including people from mathematics, economics, and computer science. For some people who don't work in this field, all of these fields look extremely different from each other, right? So if you're thinking about what are the possible connections between these fields, hopefully my talk is going to highlight some of these connections. So let's start. So just to give you a little bit of background, I'm currently in Sydney. So just to give you a little bit of idea, I'm at UNSW Sydney right now, which is on the eastern side of city of Sydney. And right now, one thing which you can relate to is that just 10-15 minutes away is the Sydney cricket ground where the Sydney Test is happening, where we are doing quite badly at the moment. I did go on day one, but after that, I might drop by tomorrow. So this is the UNSW campus, and I already discussed that my secondary role as at the UNSW AI Institute, so I won't go into details. So I wear a lot of hats, and one particular hat that I wear is a lot of scientific service for various journals. And the reason I have this slide is not to say that I'm editor or associate editor of this and this journal, but just to give you a very strange snapshot that basically I serve as an associate editor for social choice and welfare, which is typically viewed as very far from computer science, right? It's a subfield of economics, welfare economics, and it's all about voting or trying to make collective decisions which are fair. Why this is connected with multi-agent systems will become clear very soon, but in multi-agent systems as well, we have multiple stakeholders. These could be humans, these could be bots, they could be drones, whatever entities there are in a multi-agent system. You may want to make sure that they are making decisions in some principled way. So that's where some ideas, some social choice theory come into play. Other than that, multi-agent systems is just one of the branches of artificial intelligence, which is a very big, broad term which is used for many different things. So I don't do too much of machine learning in my own research. Basically, I am a trained theoretical computer scientist who designs algorithms which satisfy certain axiomatic properties. These typically I'm looking at problems which are in a multi-agent context, and many a time we are using ideas from mathematical social sciences, social choice theory, and game theory, which are very well established field as many of the participants mentioned. It's since the time of John von Neumann, John Nash, and so on. So that's a little bit on the background. And coming to my talk, even if you don't work in this area, I'll just try to motivate in a way so that it's approachable for anybody. Basically, what we're trying to do is we are trying to answer the question, who gets what? Now, this is a fundamental question which comes up when, let's say, there are kidneys to be allocated to patients who need kidneys. It's a question which comes up when job positions need to be given to job applicants, university positions to students, or during emergencies or during COVID vaccine time, hospital beds to patients who are on a waiting list. So many of these ideas are captured in a very nicely written book, which is not a very technical book. It's actually a book which has a lot of historical context. It's a book by Stephen Brams and Alan Taylor, which is called Fair Division from Cake Cutting to Dispute Resolution. So even if you're not, you don't have a mathematics degree or you're not a researcher in this area, I think this is a book which is quite readable. It's something which will be quite interesting for many of you. So in this particular talk, what I'll try to do is I'll try to explain a few aspects which have actually led to Nobel Prize in Economic Sciences, which was awarded to Al Roth and Lloyd Shapley in 2012. And just to emphasize that this area of algorithmic market design is something which is quite influential. It's also very influential in designing various kinds of auctions, in particular spectrum auctions. And again, one reason for having this slide is that just wanted to emphasize some of the real world applications of these results. And also this book, the Discovering Prices book that I have on the slide, this is again a popular science book. So if somebody is just trying to get familiar with this field, please check out this book. And similarly for this particular prize as well, Al Roth, after his Nobel Prize, he wrote a general interest popular science book called Who Gets What and Why. And that can be viewed as a readable version of some of the ideas I will explain today. So as far as my particular talk is concerned, I hope I can give you a glimpse into algorithmic market design. I mentioned maths, computer science, and economics, three fields. Sarma did ask me a couple of questions about the mathematical foundations of computer science, but hopefully in this talk, I will highlight this math CS connection and also the CS economics connection. I will try to make, at least I will try to familiarize you with some key concepts and an increased appreciation of what is called the axiomatic method in social sciences, or social choice in particular. I will give you a glimpse into a couple of influential market design algorithms. These are very basic algorithms. These are just used as basic tools, and they have been extended and they've been generalized in many different ways. But the key ideas from these algorithms are already in the basic versions of these algorithms, and I hopefully by the end of this talk, you will understand these algorithms quite well. So let's start with something which is even more classical than much of game theory, which is this problem of an allocation problem. So again, I start with the motivation. Let's say you have 4 patients, patients 1, 2, 3, 4, who are in need of a kidney. There are four kidneys, kidney A, B, C, D, and the compatibility of a particular patient with the kidney is illustrated with these edges. For example, patient A has a line going to kidney A and B, or an edge going from to A and B, which shows that patient 1 is compatible with kidney A and kidney B. Similarly, patient 2 is only compatible with kidney C, and patient 4 is only compatible with kidney A. Now, in this kind of situation, when you have patients who are not compatible with all the kidneys, you do want to save as many lives as possible, right? So, how can we match the patients to kidneys is a very important problem, which has actually solved many times in many complex ways across the world. What is nice is that actually solving this problem has been studied in very basic discrete mathematics, graph theory for a very long time. And the idea is simply to view this problem as a graph. I already illustrated it as a graph where you have vertices on the left side illustrating the patients. The vertices on the right side, they are representing the kidneys, and the edges basically illustrate the compatibility relations between patients and kidneys. And basically what you're trying to do here is you're trying to find what is called a maximum size matching of this particular graph. And the moment you find a maximum size matching of this particular graph, that will give you the guidelines that which particular patient should get which particular kidney. So this is obviously well studied in matching theory. The reason I'm trying to connect this is because I want to highlight that some of the very basic aspects of discrete mathematics graph theory are foundational tools when we're doing all this algorithmic market design. So I won't go into too much technical detail, but basically when you have these lines or what are called edges, a subset of these edges is called a matching if each vertex is incident to at most one edge which is selected in the matching. For example, in this figure, this blue line is called a matching because of the property that I have described. This particular set of blue edges is not a matching because there are two blue edges which are incident to vertex 1. So this is not a matching. And obviously we are trying to find a matching which is of maximum size, and this is one matching which is of maximum possible size because every particular vertex is matched. So in this particular matching, 1 gets B, 2 gets C, 3 gets D, and 4 gets A. And this particular matching, if you find it, is also quite useful because that is what's going to tell you which patient should be getting which kidney, and you're basically solving the maximum number of lives. So this is just to highlight that matching theory is very important in some of the things we do. Obviously, this is very classical. This is there's one very nice book which I highly recommend if you're into discrete mathematics. That's by Lasher Lovash and Michael Plummer, which has wonderful proofs and a lot of details on matching theory. So I'll just give one example on how some of the very fundamental aspects in like fundamental mathematical lemmas and theorems, they give you guidelines on how to design desirable algorithms. One particular lemma is called Bird's lemma, which simply says that a matching is of maximum size if there is no augmenting path relative to matching M. Now, I haven't defined what an augmenting path is, but let me just give you an intuition. Basically, augmenting path is a situation where you start with a free vertex, then you toggle between an unselected edge, selected edge, and then unselected edge going to a free vertex as well, which is the case in this figure. And now if you replace the blue edge with the two black edges, then you get a matching which is of larger size. So what Bird's lemma is telling us is that once you don't have a situation where you can't toggle and get an improvement, then basically you have arrived at a global matching which is of maximum size. Now, this very simple idea, it has an elegant proof. It also gives rise to an algorithm where you can simply keep on checking where you have an augmenting path. If there is no augmenting path, you're done. If there is an augmenting path, you just implement that augmenting path. And by doing that, you can find a maximum size matching, which also gives you a nice solution to this problem I motivated earlier. Now, some of these ideas can be used in some of the problems that we work on. When I mention markets, people typically might consider prices, but markets do not necessarily have to have prices. Markets are any kind of scenarios where you might have some supply and demand. So even this particular problem where you have these kidneys and you have patients is a situation of a kidney market where you have supply and you have demand and you want to somehow clear that market to satisfy as many people as possible. So that's one connection that I want to highlight, which is a very basic connection between graph theory, discrete mathematics, and some of the problems that we look at in algorithmic market design. So the next problem that I'm going to motivate is an exchange problem. And again, it's from some kidney exchange motivation. Say you have a situation where there is one patient who already comes with a corresponding donor. Recipient 1 has a corresponding donor, but that particular donor's kidney is not compatible with recipient 1. And similarly, recipient 2 has a donor who is some loved one, for example, a family member who wishes to donate a kidney to recipient 2, but because of some blood type or some compatibility problems, donor 2 cannot donate the kidney to its family member. So one nice way to help all these people is to enable exchanges of organs. This is a very simple scenario where, let's say, donor 2 can give the kidney to recipient 1, and donor 1 can give their kidney to recipient 2. And in this way, two families have helped each other to make sure that two lives are saved. So this is one particular problem that we will look at, which is abstractly written as an exchange problem. Now, why do we call it an exchange problem? That's because we have each person coming with their own object, and the goal is to potentially exchange items among the people to get some mutually beneficial exchange. So I'll just stop for a second and just emphasize that if any of you have some questions, please feel free to interrupt or ask me so that we're not lost. So in this particular exchange problem, what we have is a situation where not only do agents own their respective items, for example, agent I owns item OI, but agents also have preferences over which items they might want. That can be the case in compatibility situations in kidney exchange. For example, sub-kidneys are more compatible than others. Or it could be the case that all you're doing is you're basically asking people to exchange their office spots. You have an open space office, or you have some closed offices, and people within the offices, do they have an incentive to exchange their spots to get something which is better for them? So in that case, what you often do in social choice is that you ask people what their preferences are. And these preferences are represented in a sort of a linear ordered list, which is basically saying, for example, agent 1's linear order says that O2 is the most preferred because that's the leftmost. Then you have O3, and then O1, and then O4. So all of these lists that I have mentioned on this page are essentially preference lists, which show that which particular item is the most preferred, which item is the second most preferred, third most preferred, and the fourth most preferred. So that's how we get the information. Now that we have this information, what do we want to do? We want to decide which particular agent gets which particular item. Note here that agent 1 already owns item O1, agent 2 already owns O2, agent 3 already owns O3, and agent 4 already owns O4. And we are basically considering should some of them exchange items among themselves to get something which is better for them. So I'll ask somebody to make a guess, like who should get what item. Does anybody want to have a go at this particular problem? If you have the situation, which particular item should agent 1 get, for example?
Patient 1 should get object O2 because no one else wants O2. No one else wants O2 as in the sense that it's not the most preferred object. Similarly,
yeah, that's a reasonable argument that agent 1 likes O2 and nobody else likes O2 that much, so let's give agent 1 O2. I can go with that. That's one argument you can make for why agent 1 should get O2. Any other ideas? For example, which particular item should agent 2 get?
Agent 2 should get O3 because no one else wants O3. And 3 and 4, well, 3 wants O1 and 4 also wants O1. And the second one is O3 and fourth one is O4. So if we give O3 to 2, we can give O1 to we can give O1 to 4 and O4 to 3.
So you're suggesting that O1 should be given to whom? 3 or 4?
O3 should be given to 2 and O1 should be given to 4. 4, yeah.
Okay, that's a reasonable suggestion. Basically, my motivation was to get you thinking on who should get what, right? That's the fundamental question we're starting with. And one way to do this is by just looking at something and saying, okay, somebody most prefers this, let's give it to that person. But the question is, how do we make these decisions? Do we just look at this particular example and then say that, okay, this looks like a reasonable method? Or is there another way we can go about it? And that's what we will explore in this particular talk, which is highlighting some very general ideas, which we say that these are principles we want to achieve or satisfy, irrespective of which particular problem instance or which particular example we have. And that particular thing goes back to one of the audience members who asked that why should we look at these issues about morality or ethics and bring them into mathematical decision making. This is exactly what we're going to do in some very constrained way in the next few slides. So the first particular principle that we will go with is what is called individual rationality. Now, individual rationality basically says that outcome should be at least as preferred by each agent as their backup outcome. In this particular context, what we basically require that no particular agent should come to the market with their particular item and then go out of the market by getting something which is even worse. Now, no person will find this reasonable or acceptable to participate in a process and then get worse off by participating in the process. That completely defeats the purpose of participating in a joint collective decision-making process. So this is one general idea which has been around for a long time in mathematical social sciences, which can be very rigorously formalized as a mathematical axiom in particular context. In our context, basically, it requires that agent 1 should either get O1 or it should get something which is better like O3 or O2. It should not get something which is O4. This particular axiom is already telling us that what are the certain requirements on the outcomes. So that's the first axiom that I want to emphasize. Some people might say this is not a desirable axiom. That's obviously a normative discussion. But I just want to emphasize that this is something which is quite minimal. It's something which a lot of people would say should happen. And this is one of the target properties that we will go for in this particular decision-making process. The next one is called Pareto efficiency. And again, this has been around in mathematical economics, mathematical game theory for a very long time. In fact, this was proposed by an Italian polymath at least 200 years ago, Wilfredo Pareto. So this concept is named after this polymath. And the Pareto principle basically requires that whatever outcome you get, that particular outcome should be such that there should be no other outcome that is weakly better for everyone and strictly better for at least someone. Again, this is the concept which basically emphasizes that there should be no unambiguous improvement. So the outcome should be optimal in the sense that you should never have a situation where everybody says that actually we don't mind getting some other outcome which is weakly better off for all of us. And one of the persons says that actually they get a strict improvement. So again, this is a principle which has been around for a very long time, and this is a principle that we pursue in many different social choice market design contexts because it basically encapsulates some sort of very weak efficiency. A collaborator of mine, Hervé Moulin, with whom I've written several papers, he's not a computer scientist, he's actually an economist. He also wrote a very influential book called Fair Division and Collective Welfare. He actually goes as far to say that Pareto efficiency is the single most important tool for normative economic analysis. So if you're looking at any kind of market and you're going for an outcome which is desirable, the case that has been made by many economists is that the outcome should be Pareto optimal, because if the outcome is not Pareto optimal, then obviously you can get this kind of improvement. So up till now, I have emphasized two concepts which hopefully are not very controversial. They've been around for many years and they are explored in this market design context as well. I will go with one other concept. This is again an axiomatic property which is not particular to this particular example. This is a principle which captures a very important aspect of stability. And that concept is called core stability. It's similar in the sense as Pareto optimality, where Pareto optimality concerns everybody deviating and finding something which is weakly better or strictly better. In core stability, you even allow deviations by not just the set of all agents, but you allow any sub-coalition to deviate. And it basically requires that no coalition of agents can deviate and obtain a unanimously better outcome by cooperating within the deviating coalition. So this is again a concept which has been extremely influential in mathematical economics. And nowadays in many computer science applications, we use this concept as a guiding principle to find outcomes which are stable in this sense. So in this particular book, which is a very nice book, popular science book on game theory, basically more than a dozen influential game theorists were asked 5 questions about some of the influential ideas in game theory, and at least some of them, they mentioned core stability as one of the influential ideas. So in my particular work, where I'm often coming up with algorithms which should satisfy some desirable normative properties, often we do get inspiration from these ideas such as individual rationality, core stability, etc. And if you notice, all of these ideas are directly applicable to this particular problem that I have just defined, which is this exchange problem, where we want to exchange items among the agents, and we want to do it in some desirable way. So some of our guiding principles, or what I call axiomatic properties, include individual rationality, Pareto efficiency, and core stability. So these are the kind of outcomes we're after. One other property that I haven't described, which is not a property of an outcome, but rather it is a property of a function or an algorithm or a rule or a protocol, is strategy proofness. I believe Sarmad gave a talk on top trading cycle a couple of months back, and he did discuss strategy proofness, but just in case somebody hasn't explored that particular talk, I'll just mention that strategy proofness is a very influential concept in mathematical economics, which is all about eliciting truthful information from people. Note that in our problem, what we are asking people is to express their preferences over which items they like more, which items they like less, and so on. Now, if people lied about their preferences, there would be no point of doing all kinds of fancy optimization, because you would be doing optimization on the wrong input. Also, if some particular problem can be gamed in this way that people may have an incentive to deviate or lie about their preferences, it is creating an uneven playing field among agents who may have more information versus agents who have less information. So these are just two reasons why strategy proof is important, but there are many other reasons as well. And the main definition of strategy proofness is that agents should never have an incentive to misreport their preferences to obtain a more preferred outcome. So you should never have a situation where somebody gives information to the system, and by deliberately lying about that information, they actually get an outcome which is better than what outcome they would get if they lied, if they reported truthful information to the system. So that's yet another property that we are typically after when we're designing these market design algorithms. Now let me share one very nice, elegant algorithm that is due to David Gale, mathematician called David Gale, and he came up with what is called the top trading cycles mechanism or algorithm, which enables exchanges of items, and it's highly desirable. Why is it desirable? Well, it's desirable because top trading cycle satisfies all the nice properties that I have defined in the previous slides. It's strategy proof, and it gives an outcome which is Pareto efficient, individually rational, and core stable. What is even more special is that it is the only algorithm that satisfies these properties, which is basically saying that there is no other algorithm which satisfies these properties. So this is often called a characterization result. This particular characterization result was proven by Ma a long time ago, who's a researcher at Columbia University. A colleague of Ma, who's J. Sethuraman, who I was visiting just a couple of weeks back, actually shared with me a simplified version of the classical result, where he showed that in just a couple of pages or so, it can be shown why top trading cycle mechanism is the unique algorithm which satisfies Pareto efficiency, individual rationality, and strategy proofness. But I believe that Sarma did prove some of these axiomatic properties in his talk. He can interrupt and let me know what exactly was covered.
So not the last one that you said, and not core stability either.
I see.
Yeah.
Okay. So now that I've at least tried to make a case that we do have an algorithm which is desirable, let me actually explain how the algorithm works, and it actually works in a very elegant and simple way. And again, we will be framing that algorithm in the form of a graph. We'll be using graph theoretic techniques. So again, it highlights the fact that for solving some real world problems, some fundamental knowledge of discrete maths, graph theory, and combinatorics is very important. So
there's a
how do we
question.
do?
Oh, hold on.
Yeah.
Okay, just for my clear understanding, can you give us some simplest non-trivial example of Pareto efficiency from daily life? If it is very, very important, daily life does not mean, it could include stock exchange or whatever, but it should be like simplest non-trivial example.
Sure. So let's say that your family wants to go for dinner tonight. It's Friday night, and you want to go for dinner tonight, and all of your family members have different options where you want to go. What you don't want to come up with is not a restaurant where you go, where actually just one street away there's another restaurant where everybody says that actually I don't mind going there, or and one particular family member said that actually I prefer going there. In that case, what you have done is you've made a suboptimal decision, and a decision which is not Pareto efficient, right? So that's a typical example where any kind of daily life decision making that you do not want to come up with a decision which is not Pareto efficient.
The example of non-Pareto efficient, that is very clear. Now, the example of Pareto efficient decision, I mean, this is.
Yeah, so it's just a negation, right? So you never want to have an outcome where there exists another outcome which is weakly better or strictly on one is strictly better.
So in the example
So
of the
it's just
same.
defined in that way. Basically it means that you have to compare your outcome with all other outcomes, and you don't want to have the situation that you get an unambiguous improvement. That's how the definition is.
The best thing is never take a decision.
Sorry?
Never take a decision.
Never take a decision. That can be that might be highly inefficient, right? Because maybe all family members are hungry, they want to go to the restaurant and have food. So not making a decision and not going to the restaurant and not having something at home might be highly undesirable.
Go ahead. Yeah.
All good. All right, so we are going after these properties, and the way we view it is as a graph. We basically put all the vertices and all the items as vertices in the graph, and we do have some directed edges in the graph. So how do these directed edges work? Well, every item points to its owner, which means that O1 is going to point to agent 1, O2 is going to point to agent 2, O3 is going to point to agent 3, and O4 is going to point to agent 4. And the agents also point to items. So every agent points to the most preferred item that they like. For example, agent 1 likes O2 the most, right? So agent 1 is going to point to O2. Agent 2 most prefers item O3, so agent 2 is going to point to O3. So what you have now is a graph, and what you also observe is that every vertex in this graph has an out degree of exactly 1. And anybody who is vaguely familiar with some aspects of graph theory, you would know that the moment you have a graph in which every vertex has an out degree of 1, you are guaranteed to have a cycle. In particular, in this case, you have a cycle which is marked in this bold part where you have all these edges which are highlighted. Now, in the cycle, what you do is you simply give each agent the item that that agent is pointing to in that cycle. So O1 gets O2, 2 gets O3, and 3 gets O1. And after giving these items to these agents, you basically just ask them to go away, they're done. So they're done. And after that, for the remaining agents, you simply ask them to point to the most preferred item that is still in the graph, and there's only one item left, so obviously 4 points to O4. It's a trivial cycle, 4 points to 4, O4 points to 4, and that's the end of the story. So 4 just gets O4 as well. You implement that cycle and you're done. So this is how the top trading cycle algorithm works. I just wanted to give you a quick snapshot, and basically the nice thing about this algorithm is that it satisfies all these desirable properties. Now, this top trading cycle algorithm is a basic building block for many different exchange markets which are operating around the world. And some of these ideas have been used in some kidney exchange markets as well. So that's a little bit on the motivation side. The next particular problem that I will go towards is another allocation problem, which is a bit different. In this problem, yes?
Haris, just I wanted to make a small comment. I think the longest cycle, the biggest cycle that has ever been realized in kidney exchange is like 20 patients.
Wow.
Yeah.
I was aware of 12 or 14, but I wasn't aware of that cycle.
Yeah, this is when I was preparing the talk. I
see.
Stumbled across it, and that's absolutely amazing that 20 families each helped out and 20 people, were better off without any exchange of money, right? All those families, their loved ones, had a better chance of survival. So it's
Exactly. I think this, I don't know how far we are in Pakistan regarding this. I am currently at University of New South Wales, which has a co-located hospital where one of the world experts in kidney exchange markets, Paulo Ferrari, he sits there. So he has had some exchanges which are at least 6 patients at the same time. And again, what I want to highlight here is that like collectively using all the information, then collectively making these decisions which are actually beneficial to people is one of the goals of many of these ideas. And what is interesting is that whereas the ideas from social sciences, such as in game theory, are guiding principles on what kind of algorithms we should design, the way we are designing the algorithms, they are using all the framework, terminology, and ideas from graph theory. So it's a nice combination where ideas from mathematics on one side, axiomatic results from game theory, and algorithms from computer science, they all combine together to come up with some nice results. These are mathematically beautiful results, right? But they're not just mathematically beautiful results, they are actually also helpful in solving many exchange problems which are important in real life. All right, so the next particular problem I'm going to look at is again a very classical problem. If some of you have looked at the men-women stable matching problem, it's similar to that. It's basically a problem where this time items are to be allocated to agents, but agents are not endowed with, or they don't own those particular items. But it does have some other features which are not present in the other one. So let's say you have hospital positions which doctors want to get. One doctor prefers one hospital, another doctor prefers another hospital, and so on. So what basically we have is a situation where doctors express their preferences over which particular hospitals they want. But you also have a situation where hospitals express priorities over which doctors are more qualified for their particular hospital. So it's a two-sided matching problem where both sides express some information about which entities are desirable on the other side. Now, this kind of situation is not just related to doctors and hospitals. It's a situation which happens in schools and students. It's often is the case in job markets as well, right? When you have all kinds of employees and employees, and rather than do it in a very decentralized way or in a very ad hoc way, you might want to have a situation where you express these preferences and then you make some joint decisions on which particular student should go to which particular school. So this is often a problem which comes up in centralized admission markets. And why is it called a market? Again, it's a problem which has both a supply and it also has a demand. So again, as we often want to do as computer scientists, we want to abstract the problem mathematically to make it it's much simpler to analyze and think just in terms of some mathematical objects. And the mathematical objects in this case are just preference or priority lists. So this is a very simple example where you have 3 agents who have preferences over 3 items ABC, and you have 3 items ABC who have their respective priorities over agents 1, 2, 3. For example, agent 1 has a preference list where B comes before A, then A comes before C. So B is the most preferred item for agent 1, then A is the second most preferred item for agent 2, and C is the least preferred item for agent 1. Again, this is a different problem, right? It's not an exchange problem, but the question stays the same. Who should get what? Again, I'm happy to take some guesses or suggestions on who should get what. I think we had one audience member who was very sharp and he was able to give some very good ideas. So maybe he can have a go at this.
you know the previous algorithm you described. What if we use it for both the hospitals and the doctors, and then look at the similarities between them? So if it's overlapping, then you give it to them. Rest you make the cycle again, and then you overlap it. Eventually, you get the answer.
That's possible. I'm not sure what axiomatic properties it's going to satisfy, but you could do a few things which you mentioned. Like one could be that you try to give the most preferred item to an agent, but do remember now that the method that you described, it's sort of ignoring the fact that items also have priorities over agents, right? That's something. There's an additional information here which is not covered in that exchange problem that we were discovering before. So how do we take care of that? That's one question we need to be very mindful of. But again, I don't want you to think of just this example. There could be many solutions for this example. We are not concerned about just making sure that this example is done right. What we are after are some general principles which will be guiding lights for how we should be doing that as a general algorithm. So just like Pareto efficiency was one principle, we could even apply it here, right? What other principles can be applied? That's one question I want you to think about. So the guiding axiom that has been very influential in this particular problem is the following one. So before I highlight the guiding principle, let me give you an idea of how we get that guiding principle. So let's consider this arbitrary allocation where 1 gets B, 2 gets C, and 3 gets A. I want your feedback on whether this is a good decision or not. Does anybody have any idea whether this is a good decision? Is it good for anybody? Is it good for agent 1? It looks like a good solution for agent 1, right? It's agent 1 is getting the best.
Yeah, if I'm not mistaken, this is just the Gale-Shapley algorithm, so it's going to be preferable for the people, the active proposers in the situation than the passive people. In this case, the applicants are going to be better off than the hospitals.
Yeah, so exactly this problem is very closely connected in some way mathematically equivalent to the algorithm. But right now, I don't want to discuss the algorithm. What I want to do is I just want to identify what is the desirable property that we're after. There could be many algorithms which could satisfy a particular property, right? But just like we identified individual rationality, I just want to understand what should be the right principle that we should apply here, which is independent of an algorithm, right? Algorithm is something which might satisfy an axiom or it might not satisfy an axiom, but that comes later. The thing that I want to motivate here is that in many of these problems, what many of our core researchers are doing is that they're first identifying what is the right principle we want to use before they start coming up with a particular algorithm.
Oh, all right. So in this context, then what you want to avoid is an unstable pair where you have a doctor and a hospital where the doctors match with the hospital that they don't, such that there is a hospital available that the doctor would prefer to the one they're currently allotted to, and similarly, there is a doctor available that the hospital would actually prefer over their currently allotted doctor.
Absolutely. So the next slide exactly captures this idea of stability. In this particular context, it's called something slightly different, but it's exactly the same idea of stability. So what we don't want, now I'm going towards an axiom which is called justified envy freeness. Now that particular axiom is defined by mentioning the violation of that axiom. So basically what we don't want is the following situation where agent I is matched to O prime, agent J is matched to O, and you have a situation where I would rather be matched to O, and O also thinks that I is a higher priority agent than agent J. So this particular matching that we have is undesirable because both I and O would rather be matched to each other, right? And now this is Why is it a desirable property? I can give you one normative reasoning, right? Because I and J would feel that, look, we prefer to be with each other. Why aren't we? Yet another normative example, actually a legal argument I can give is that in many systems, you don't want to have a situation where a student says that I would rather be admitted to O, and O, instead of accepting me, has accepted somebody who is actually lower in the ranking. That would be a completely disaster, right? In terms of legal lawsuit, student I's family would say that, look, we have been unfairly treated because something is wrong with the system. So these are the ideas that we are after, and this is exactly one of the main properties that we use as a guiding principle for many of the algorithms. So in the next few slides, I'm going to explain one version of what was mentioned as the Gale-Shapley algorithm. There are actually two versions of the algorithm. One is called the agent proposing deferred acceptance algorithm. Then there's another one which is called the item proposing. Often it's in the classical paper by Gale and Shapley. This paper was written in the context of men and women, but we are in this another application, but the mathematics is very similar. So how does this algorithm work? Again, this is a non-technical talk. So just like the top readings cycles algorithm, I will not give you the pseudocode. I will not give you a technical definition of the algorithm, but what I'll do is I'll exemplify it by a simple example. The idea is very simple. The agents from one side, they make proposals to the other side. Items choose the best partner agents from among the available proposals, and they reject others. Now, obviously, if some agent is rejected, they have to resort to applying to the next most preferred item in that case. It could be the case in some case that they run out of items in which they are simply unmatched, which means that they did not get into the required hospital or school or company that they were after. Main thing is that this is a very general problem. It can, depending on the application, the agents could be students, they could be doctors, they could be employees. So in the literature, this is often written in the context of school choice, where the agents are basically students. And the algorithm that I will briefly mention now is an algorithm which is strategy proof, which means that no student has an incentive to misreport their preferences and get a better outcome. And it also satisfies justified indefiniteness and what is called constrained Pareto efficiency, which is Pareto efficiency within the set of outcomes that satisfy justified indefiniteness. So how does this algorithm work? I will just give you a very quick intuition. I don't want to go into too much detail. I'm not sure how I'm doing with time. So the way it works is that agents, they apply to the most preferred item or school. Obviously, if there are multiple agents who apply to the same school, then the school needs to make a decision. In this case, for example, agent 2 and 3 both think that A is the most preferred school. So A school has to make a decision, and obviously agent school A is going to reject 2 in favor of 3 because A prefers 3 over 2. So throughout this process, what we do have is a tentative matching, and this tentative matching keeps on changing because obviously some agent is rejected, they have to apply to another school, and so on, and this process continues. But the main thing you need to observe here is that during this process, every time the school either gets a new proposal, in which case it can either keep the original match or it can replace it with something better, or a school hasn't had any student yet and it gets an extra student. So what is going on is that the schools are always improving during the process, and because of this reason, the process terminates in a matching. In this case, the matching is going to be 1 being matched to A, 2 being matched to B, and 3 being matched to C. And that, what I mentioned, is actually a mathematical proof in just a single line. You don't need any mathematical symbols. You don't need higher mathematics. I know there are some distinguished professors here who do group theory. We don't need any higher mathematics. This is just a one-line English proof for why this mathematical argument terminates. So obviously in each step, each school either gets the same match or gets an extra student, or the same school gets a better replacement for a student. This process cannot continue, right? Because this is a preference list, and at some point you have to stop, and that's why the algorithm terminates. So in the original paper where this particular algorithm was examined by Gale and Shapley, I just want to mention, because this is a general audience, after presenting this algorithm and its properties, both Gale and Shapley, they start getting into a philosophical discussion on the nature of mathematics. And one thing that I really like here is that they say that most mathematicians at one point or another have probably found themselves in a position trying to refute the notion that they are people with a head for figures, or they know a lot of formulas. At such times, it may be convenient to have an illustration at hand to show that mathematics need not be concerned with figures, either numerical or geometric. And then it has some very nice quotes here, that what then, to raise the old question once more, is mathematics. And Gale Shapley take is that the answer it appears is any argument which carries out with sufficient precision is mathematical. So I really want to emphasize this, because you don't have to be a mathematics undergraduate to appreciate an argument which has been made in a rigorous manner, right? It need not use Greek symbols. It just needs to have some implications, some deduction, and it just needs to be done in a precise way, so that for everybody it's clear that this argument makes sense and it's establishing some statement that you want to prove. So that's some nice discussion in a technical paper that was written a long time ago in 1962. Right, so just to give you some references, in case somebody wants to look up some further work on this particular topic, there's one work, this is one paper which is very influential. It's written by a couple of economists, Abdul Qadir Roglu and Sonmes, School Choice, Mechanism Design Approach. And the other is a very nice long survey article by the Nobel Prize winner Al Roth, where he talks about deferred acceptance algorithms, their history, the theory, practice, and open questions. Although, well, this was published in 2008, so I expect most of the open questions are already answered. Okay, so in case some of you are interested in some of this work, some of my colleagues in Europe, especially Peter Biro in Hungary, they maintain a website. You can Google matching in practice, and you can find out so many different applications of matching market design in different contexts. So what they do is they keep track of many different applications. They understand what's going on in real life. Often real life interventions are not based on necessarily on deep mathematics. It's basically realizing that there is some real life system which is not working as well. Maybe it's not Pareto efficient. Maybe it's not satisfying some legal requirement, which is like justified Henry freeness. Or maybe there's some way that people can be, many stakeholders can be made happier by advising some small tweak in the algorithm. So all of these are part of matching market design, where you don't always have to come up with a completely brand new algorithm, but small interventions can be extremely helpful when there are hundreds of participants in a system and they're making use of some school choice or hospital resident matching market and so on. If you can somehow identify these flaws in some real world systems, it could be in your local university system. It could be in any of the more you ask around, often systems have their own particular constraints. They might have some further real world constraints, and these give rise to new problems as well. So some of these interventions can work out in your local context as well. So what I advise you to do is look at how the system is working at your faculty level or school or university. Are they doing it in a right way? Are they even satisfying some axiomatic properties, or are they just doing it in a completely ad hoc, non-rigorous, unprincipled way? So these are all opportunities for you to either come up with a new mathematical problem or simply use existing mathematical ideas to have some intervention and some real world impact. So both are useful and important. Speaking of real world impact, or at least looking at problems around you and coming up with some new algorithms, the next algorithm I'll explain. I'll just quickly go over it because I don't want to take too much time. But the reason I want to mention this is because basically this algorithm borrows from a lot of the ideas I've already explained in the previous slides, but it basically came up during the COVID pandemic, where many people started thinking about how to do rationing under priorities in a principled way. So this is a problem which comes up in various triage scenarios where, let's say, you have an overflow of patients in some hospital, and you do have some guidelines in the hospital that a certain number of hospital beds need to be allocated to healthcare workers. Certain number of hospital beds are prioritized for, let's say, young people or very old people, because these are two vulnerable populations, right? So who should be saved when you ideally, obviously, in an egalitarian society, you should not have a situation where you have to make decisions, but there are over constrained scenarios in many, even in developed countries. But how do you make these decisions? Should these decisions just be made in an ad hoc way, or should we be borrowing ideas from fair division, game theory, etc., and trying to formalize axioms and trying to come up with methods which are principled in some way? So this was something which motivated some of our community members in the market design community. And the next few slides, I will not go into detail because I don't know how I'm doing with time, Samad.
I think you're doing okay.
All right, okay, I'll spend a few minutes then. Yeah. So the problem that came up was a problem where you have a set of agents or patients. You have now what is called homogeneous resources. So all the resources are exactly of the same type. For example, hospital beds or vaccines. So agents don't care. All they want is to get one unit of that homogeneous resource. But you also have what are called categories, which are basically resources have categories, and these categories have priorities over agents, which also specify which agents are eligible for that category. So let me just make this clear with the help of an example. Say you have a situation, there are 4 patients, 1, 2, 3, 4. There are 2 hospital beds, and let's say they have 2 different categories, C1 and C2. Category C1 says that patient 1 is most important, then patient 4, then patient 2, and that particular category does not mention patient 3 because maybe patient 3 is not eligible for that particular category. For example, it could be the case that category 1 is for elderly people and patient 3 is a young person, so that particular category is not going to allow a young person to use that category, which is especially for elderly people. There might be another category which is just for healthcare workers. So category 2 might say that agent 1 is the most preferred prioritized patient, and then agent 3, and that's it. So question is that out of these 4 patients, which particular patient should get which particular bed from which category, or which particular category should be matched to? So again, the question is who gets what, right? And obviously 2 people will be matched to the category and 2 people will be unmatched. So again, just like I've been emphasizing, the underlying mathematical structure is again a bipartite graph where the eligibility requirement can be captured by these edges, right? So 1 has dotted edges going for C1 and C2 because 1 is eligible for both categories. 4 only has an edge going to C1 because 4 is only eligible for C1, it's not eligible for C2. And basically what we are going after is we're trying to find a desirable matching, which will obviously only match 2 patients here, right? Because there are only 2, the upper limit for category 1 is 1, and upper limit for category 2 is 1 as well. So one potential outcome is where 2 is matched to C1, and yet another outcome is that 3 is matched with C2. That's one possible way. But again, the question arises that is this the best way? Would somebody complain? Is some legal aspect being ignored? Can we borrow some results or ideas from previous work and identify which are the desirable properties? And indeed, some of the classical works from market design immediately apply to this fresh problem that came out, especially during COVID pandemic times. But you can still use ideas which are from market design. So one is just compliance with eligibility requirements. Obviously, a patient should get an item from a category which it's eligible for. The respect for priorities of categories is yet another axiom which is very similar to the justified arbitrariness axiom that I defined earlier. Basically, what it says is that you should never have a situation where I does not get an item, but J gets an item from category C, but category C thinks that I has a higher priority than J. So that's obviously an undesirable situation because I would think that I has been unfairly dealt with because I deserves more than J to get an item from category C. And thirdly, because these are very important scenarios where you want to use as many resources as possible, you want to find a maximum size matching as well, which satisfies eligibility and compliance. So we're after these three properties, and basically we came up with an algorithm. This is joint work with Florian Brandl, who is now a professor at University of Bonn, but at one point we shared a group in Germany as well. So the algorithm that I will quickly gloss over, I won't go into detail. Basically, the main idea is that particular algorithm, it specifies a baseline ordering. Then it goes in the reverse direction of the baseline ordering and tries to remove agents and add them to the rejection set. And it stops when you can't reject anymore without compromising on what the maximum size property. So at certain steps in the algorithm, it's calling the maximum size matching algorithm as a subroutine. So let's say this is the case where we want to make these decisions. What we do is we first delete agent 4 from the graph. The moment agent 4 is removed from the graph, what we do is we carefully delete some other edges in the graph, especially we delete the edge of agent 2. And the reason is because if agent 4 is not going to get an item from C1, then agent 2 should not get an item as well, because we want to make sure that we respect this respect of priorities axiom. So we do that, and after that, obviously we can't delete any further. So we put back the item agent, and then we just find the maximum size matching, which is 1 getting a unit from C1 and 3 getting a unit from C2. So that's a very quick snapshot of an algorithm. I didn't want to go into detail, but the main message is that this particular algorithm, it satisfies the main properties that we after, which were maximum size property, respect of priorities, it's polynomial time, and thirdly, it's strategy proof in this context, where basically what you say is that no agent should have an incentive to underreport its position in the priority list of the categories, because agents do have some power to dictate where they are in the preference list. For example, they might say that they're actually eligible for their category. So basically what we're requiring is that no person should have an incentive to give untruthful information, and that's what strategy proofness is in this context. And we do establish that this particular algorithm, it does satisfy strategy proofness as well. Note here that I've shared 3 different algorithms which all are strategy proof, but in general, strategy proofness is not a very easy property to satisfy in many different contexts. In fact, most algorithms, if you look at them in these collective decision-making contexts, they are not strategy proof. So strategy proof is typically much harder to achieve in many of these market design contexts. If somebody's interested in, yes, Ahmed.
So when you say strategy proof, you're talking about a single agent not being able to cheat, right? What about if people collaborate, like 3 of them or a subset of them? and they misreport. Can it be proved that that doesn't even work?
Yeah, so that's what the concept that you mentioned is a strengthening of the regular strategy proofness, and it's called group strategy proofness. And these algorithms that I've mentioned, I believe, okay, so the top trading cycle algorithm is group strategy proof, but the other two algorithms are not, they're not group strategy proof. So there is a distinction to be made there.
Okay, thank you.
Yeah. So these are just some references for some work in this area. Actually, it's both these works are now published. Ours was published at EC, which is a computer science conference, and I just noticed that the paper by Pathak et al. These are some economist researchers from the Boston area. Their paper just got accepted in management sciences. So you can see that this topic is very diverse. It gets interest from people in operation research. It gets interest from discrete mathematics. It gets interest from computer science, of course, even AI and theoretical computer science. So it's a very broad area. And there's a lot of collaboration across research communities as well. So there are even papers where, for example, sometimes we write a paper where a couple of researchers are algorithms researchers. One of the researchers is somebody who's been working in social choice or market design for a long time. All right, so just to conclude, just want to emphasize that this topic is very interdisciplinary. It has far-reaching consequences. I hope I'm able to convince you that some of these key concepts are important in many different contexts, including when you're trying to decide with your family where to find dinner tonight. You don't want to have a situation which is not Pareto optimal, for example, or it's not individually rational. I mentioned a few algorithms and rules. Hopefully, some of these ideas were desirable for you. And if some of you who are more research inclined, I know this is a diverse audience. Some of the books I've mentioned here, these basically give leads into some topics where people, if they want to explore it further, there's a Handbook of Market Design. Then there's a classical book by Al Roth and Sotomayor, which is a classic economics book. Then the Algorithms for Matching Under Preferences, that's a book by a computer scientist, David Mandler, who's from Glasgow. And just recently, just a couple of months back, a new book came out which has a lot of content. It's interdisciplinary. Federico is an economist, Nicole Imorlik and Vijay Vazirani, they are theoretical computer scientists. Sarmad, I'm sure he's familiar with many of their works, especially Vijay Vazirani. So these are some nice books to explore if you are interested in this topic. And hopefully, I managed to convince you that some of these things are not only mathematically elegant, but they also have some important real-world applications. Thank you.
Questions? Okay, so I have a few comments that I wanted to make. One was that this the hospital resident problem, right? Correct me if I'm wrong, but from my understanding was that initially they used to run the algorithm which was optimal for hospitals, but then after Gail Shapley, and they understood that if they reverse the roles, so then, they'll get a... So for example, in the men and women problem, right, if the men propose, then you get a men optimal sort of matching. And so if you reverse the role, you get the other side. Similarly, in the hospital resident problem, if the hospitals are applying, then they get the best candidates. But if you do it the other way, then the residents get the best candidate. And after the Gail Shapley algorithm, they reversed it so that people were more important than the hospitals because doctors were more important.
Well, there are two. I agree with you. There are two reasons. One was obviously if you care more about the welfare of doctors, you
Right.
want to go for the doctor optimal, doctor proposing or the student proposing algorithm. But there's a strategic reason as well. So typically, hospitals or schools are in the school choice literature. Hospitals or schools are not viewed as strategic agents who are going to game the system and misreport their priorities because maybe they are bound by some merit scores, etc. Right? So if you think strategically and you only assume that the students or the doctors are the strategic agents, then the hospital proposing algorithm is not strategy proof, whereas the doctor proposing algorithm is strategy proof. So that's very interesting that it really matters which side is proposing because it also has some strategic implications.
Uh-huh. That's nice.
Yeah.
Sir, a very basic question. If you can explain in layman English, how do you divide a cake between three people fairly? An algorithm for that.
I can't summarize it in I mean, I will have to refresh my. Basically, we had what happened was that there was a Popular Science article that came out only a couple of months back, and they I had to explain that in quite a long time, like half an hour or so. I had to explain them because I was having a conversation with an illustrator. So what I can do is I can share that Popular Science article with you. Because that has a very nice illustration. But at the moment, I can't quickly convince you how it works. But there's a very simple description on Wikipedia as well. But it's the article that I'm going to share with you is probably has a very nice illustration. Basically, it works by in sort of steps where one person is asked to cut the cake into three different equally preferred pieces, and then there are some case by case analysis where if one person feels that one piece is much more preferred than other, you have to divide it into three or four different cases, but it's very short. There are still about 7-8 queries to be done, so it's not very easy to explain in just a couple of minutes. But if you want, I can share the link. There's a very nice illustration as well, and then also the Wikipedia description is very short, so you should be able to even see how the proof works just by looking at that entry.
Hello, okay, I'm Sohail, and my question is both to Haris and to Sarmad. So it seems to me very counterintuitive that for kidney exchange problem, they were like for a few years back, the number was something like 12, and now there are like up to 20 patients that can be taken into consideration. So theoretically speaking, it seems to me the n has to be infinite. It has to be infinitely large. So why is the limit of this n is equal to 20 for good kidney exchange?
No. So there is no limit. So in the US, you can either join the kidney exchange program, or you can just get the kidney of your donor. Now, if you join the kidney exchange program, then they do this algorithm for you, and the largest cycle that has ever been traded it just turns out to be of size 20 so far. So far. But there's no limit on it. I mean, in the future, it may get bigger and bigger and bigger. And obviously, yeah, theoretically, it's possible that you have n people and you get just they are all in a cycle and everybody trades. Right. But so far, the one for kidney exchange that has been traded is 20. Yeah, there's no limit in that sense. Yeah. It just
I just want to mention that there is a risk of having longer chains or cycles because if one person backs out at the end, then the whole operation which is done simultaneously, it can't happen. So there are some advantages of having not extremely large cycles.
Yeah.
There's also obviously there's also logistic.
I think in kidney
Sound
exchange,
as well, right?
yeah, in kidney exchange, there is a legal requirement that all surgeries on a cycle must be performed simultaneously.
Yeah.
And you can see why having 20 surgeries, arranging them on at the same time can be a difficult thing, right? Few surgeries are easy to arrange, so there's that aspect.
Yeah.
I want to ask, in the first algorithm you mentioned, what if we find a cycle of 2 connecting to the same dot, or multiple of the same dot? In that case, what do you do?
You mean cycle of where one agent is pointing to an item is pointing to an agent?
Yeah, the first algorithm you mentioned. If
Yeah,
two cycles of the
fine.
same size
I mean,
are passing to the same dot, what do you do?
So that's obviously a person who owns something which is the most preferred for that person. That person would never want to come to an exchange in the first place, right? That's a non-technical response to this. But as far as the algorithm is concerned, it's still a valid cycle. It's just a cycle of length 2, and it's you all you do is you just allocate you find that cycle and you just allocate the item to the agent in that cycle. That's all.
Yes, so the algorithm doesn't really care what the length of the cycle is.
Yeah.
Two cycles are connected to the same dot.
So I think his question is that so that is impossible. What you're saying, I think what he's saying is if there are two intersecting cycles, and the thing is, if there are two intersecting cycles, then one of the vertices will have out degree more than one,
Yes.
and that's a contradiction. Yeah.
Yeah.
So the situation you're saying can never happen. Okay.
Actually, the kind of questions you're asking are very valid for situations where actually I have some papers where we looked at extensions of the problem where you look at exchange markets where you have weak preferences. Weak preferences mean that you may have ties. You might say that these two things are equally preferred, right? In that case, you might have to make decisions very carefully because you may have potentially point to multiple items at the same time, and you do have to be very careful. Some of the arguments need to be done in a very careful way. So we've done work on that as well. You have to be more careful with that, and you're going towards that, so that's good.
Sir, can you please highlight difference between Pareto optimal and John Nash's equilibrium?
For Pareto optimality, I can give you an example with respect to like they're very different concepts, right? Pareto optimality says that you should always go for an outcome which is socially desirable. Now, I'll give you an example in the kind of context I've given you are collective decision-making context, right? There, the Nash equilibrium is not even well defined, right? But Nash equilibrium is defined typically in non-cooperative contexts. In our context as well, you could define Nash equilibrium by saying that if everybody has expressed their preferences, nobody would have an incentive to change their preference and get an outcome which is different. That's irrespective. That's a slightly different from strategy proofness, right? Because it could be from truthful to non-truthful or so on. So they're just two different contexts. And one thing I can point you to is that if you've explored non-cooperative game theory, the most famous game, the prisoner's dilemma, is basically showing that a pure Nash equilibrium, there's an incompatibility between Pareto optimality and Nash stability, right? There is a Pareto optimal outcome where both prisoners say that actually we should not tell on the other, right? That is the best outcome. That's the best for both of them, but it's the Pareto optimal outcome as well. But it's not a stable outcome because one of them could has a concern that the other is not going to cooperate with them. So The kind of concepts that we've been exploring are collective decision-making problems where all of them are cooperating with each other, or they're giving their information to a central organizer, and the central organizer is trying to make decisions for them. Now, in the prisoner's dilemma context, both prisoners could have done some coordination by telling what they plan to do to their friend, and the friend would make the decision for them. That's a coordination device, which is very helpful. For example, traffic lights are coordination devices as well. So, basically, I want to emphasize that they're just two different concepts. And secondly, something which is Pareto optimal may not be in Nash equilibrium. Something which is in Nash equilibrium may not be Pareto optimal.
Yes, so the way I sometimes explain Pareto optimality is I say that if you've given your kids candies, right, and if they could exchange candies so that at least one of them gets happier and nobody else, really gets sadder, why wouldn't you do that? You'll go ahead and do that exchange because, you are making at least one child happier without making anybody else unhappy. So it's not at the cost of anybody else. That's one.
I agree. That's a nice formulation.
Right, that you can make somebody happier without at the cost of making nobody unhappy. That's. Okay, so any other questions? Okay, thank you, Haris. It's been wonderful, and
thank you.
It must be very tiring for you, and we really appreciate your time and you preparing and giving us so much knowledge and wonderful. Would love to have you again, and hopefully. When you come over, then you should come to Black Hole and give a lecture over here. All right?
Sure. My wife is from Islamabad, so I'll definitely
Okay.
By.
Okay. Okay, thank you. Bye-bye. Bye.
Thank you.